This will be link will be provided, sir, in every session. Yes,
So I will start talking as if people are there.
yes, sir.
Assume that people are going to be able to watch
Yes,
this
sir.
later,
Yes, sir.
and then and also just read out the questions that were asked, and then start explaining about that.
Yes, sir.
I may have to leave in about half an hour's time, so 30, I think I'll leave.
Okay, sir.
So you can continue with any further doubts that they have.
Yes, sir. Yeah. So now recording I started already, sir. If you have some, like any suggestions or anything, you can ask. Sir. Okay, you can suggest, sir, something like related.
Okay, so a very good evening to all of you. So we are into the 8th week of the course. So we have 4 months to go. It's been a wish that I join this live interaction for several weeks now. I thought I was actually at least show my face once or twice by now, but unfortunately, because of various reasons, I've not been able to do that. But I'm really glad that I have an opportunity to address all of you through this interaction. So if you see the course, what has happened, right from the first week, we said like ray. So we looked at the ray optics picture first, and then we went on to look at the wave phenomena, the properties of light waves, so where we introduced concepts like phase and interference and so on. And then we looked at the electromagnetic nature of light. So we introduced concepts like polarization and the electric and magnetic fields, leading to modes of a waveguide and so on. So we discussed that deeply. And then finally, we went on to consider light as consisting of a bunch of particles called photons. So we looked at the properties of photons, which is sort of all encompassing, the different properties that we see otherwise in light waves. So we use the concept of wave particle duality that light exhibits. And once we defined it as a photon, we were able to understand specific interactions such as absorption and emission. So we looked at those principles initially, how at what conditions light gets absorbed in an atomic system, how it jumps from one orbital to another orbital, and from that excited orbital, how it can actually come back to the ground state, uh, emitting a photon, which could be either spontaneous emission or stimulated emission. So once we introduced stimulated emission, then we started talking about amplification through stimulated emission. And we were looking at the optical amplifiers, properties of optical amplifiers, and specifically saturation of optical amplifier, saturation with respect to the signal radiation, saturation with respect to pump radiation. So we are talking about essentially all these 3-level and 4-level systems, how things are different in these systems and so on. And once we were able to identify with optical amplification, we went on to define a laser cavity. So we basically said laser cavity is nothing but an optical amplifier with feedback. So we put mirrors on either side of the amplifier, and then we were able to make a cavity. And then we started looking at what gives the threshold conditions when that cavity actually goes from a spontaneous emission mode to a stimulated emission mode, and then what are the ways at which you're able to convert this pump radiation, the pump energy, into a signal energy corresponding to this stimulated emission of radiation. And on the spectral as well as this LI characteristics, or what is the light output as a function of input and so on. From there, we went on to understanding semiconductors. So that's what we have seen in the recent lectures. We introduced semiconductor physics and essentially how things are different from atomic system to a semiconductor system. In atomic system, we're talking about transition between specific energy levels, whereas in a semiconductor system, we are defining a valence band and a conduction band, and we are looking at transition between these bands. And so we were saying that just as how light could be absorbed between two energy levels, we could have light absorption as long as the light energy is greater than the band gap energy. And that absorption process is the basis for what we're going to see in the next week, which will be photo detection, right? All the things with respect to how we can detect light. But for now, we are looking at emission of light. So once you have an electron in the conduction band, if it can recombine with the hole in a valence band, if the band gap energy is much greater than the thermal energy, which we define as kBT, then you could have, if it's in the order of, say, an electron volt, if that is the kind of band gap energy that we have, then we have possibility of light emission. And just as we saw in the case of atomic systems, in semiconductor systems also, you could have spontaneous emission, but with proper cavity, you could convert that spontaneously emitted photons to seed stimulated emission. So you could have built-up of radiation within that semiconductor laser cavity, and you could make essentially a semiconductor laser. So people use semiconductor, spontaneous emission from semiconductor systems that is widely used, as you know, in light emitting diodes. Like to be, collimated, remain collimated over a long distance, and for that, lasers are much more used. So So in this week's lecture, we've been seeing who especially make a laser using the conductor structure. So we talked about double electrostructures, which is actually helping to not only achieve carrier confinement, but also we saw how it could be helpful to achieve optical confinement and leading to stimulated fusion. Right, so that's what we've been seeing. In the next few weeks, next 4 weeks or so, what we're going to see is next week we will see semiconductor light detection principles, how to design a photodiode. We look at basic PIN photodiode, and then we look at avalanche photodiode and so on, and how to build a receiver using this photodiode. And beyond that, we will look at principles of light modulation or manipulation of light. So we will see that light manipulation could be done by manipulating the polarization of light, or you could manipulate the phase of the light or the intensity of the light. So we will look at all those principles in a couple of weeks from now. And beyond that, we will look at the nonlinear response of material to light and using to see what's called nonlinear optics and what are the nonlinear optical principles that are useful for us. Okay, so till we complete the course. Okay. And I think somewhere in October, end of October is when you're going to have your final exams, and that is going to be an in-person exam. So at least all of you watching this will probably be registered for that. I see some 190 students that are registered for that in-person exam. And of course, that is going to be different from what you have done in the assignments. If you have done other NPTEL courses, you know that the in-person exam, you are having to be there without any other references and all that, that you need to be able to answer all these questions. So that could be a different challenge for you in that perspective. But I can try to help you in terms of visualizing how that exam is going to be. So what I typically want to get from you in the final exam is how well you have understood the concepts as far as the course is concerned. And you make it very clear that the questions that we ask in the final exam is not beyond whatever questions are already asked in the assignment. Okay, so there is going to, so you're not going to be surprised by the question itself, but what may be new to you is the fact that you have learned everything as separate modules until this point, separate weekly modules. Now you are looking at a final exam where all those modules are presented together. And in some ways, you are well equipped, or by the time you get to the final exam, you're going to be very well equipped to put together a complete system based on all the principles that you have exhausted. So, from that perspective, it could be, for example, uh, constructing a complete communication system. And but although the concept itself sounds very complicated, or oh, how do I, where do I start, and all of that, I tell you the questions themselves are not going to be that difficult because what I will do is I will break it up into a light source, a light detect, a medium in which light is propagating, and then what is happening within that medium while propagation and so on. So that way I will actually break it down for you as separate individual set of questions. For example, in the present assignment also, you might have seen a question where some common information is given and then there are multiple questions asked. So you may expect a similar sort of format as far as the final exam is concerned. And one thing I would tell you is if you have any apprehensions about the format of the questions or what the questions are going to be about and so on, you could please, converse with us through these live interaction sessions, but more importantly, use the discussion forum. And this means much activity in the discussion forum as far as course is concerned. And from that perspective, I am a little disappointed that we're not having a very good interaction between you as a student and me as a teacher or assistant. So I would urge you to use the discussion forums a little more and try to put up questions there. I just saw this message now from Ashwardhan saying that this is your first ever NPTEL exam. Well, congratulations, sir. This particularly, like I said, you would actually face a similar question, but the only difference being, you are in an exam hall surrounded by other students and you don't have much reference material in front of you. But no worries, if you have done all these assignments by yourself, if you have made a sincere attempt to solve all these assignment problems and have also for problems that you couldn't solve, you have gone back and understood the solution, you should not have a difficulty as far as taking these questions as answers. And and please you remember that we have roughly 5 6 weeks before the final exam. Use this opportunity to not only do well in the upcoming week assignment, but also going back if you had a doubt in certain say the second assignment, fifth problem, you know, please actually bring it up. You did not understand the solution for that. Please bring it up in the discussion forum and allow us to help you just clarify those doubts. Okay. Like I said, so far we've not had much discussions happening in the discussion forum, but going forward, I would really urge you to participate. And that's the only way you will learn as far as these processes are concerned. The other thing that I also want to point out is some of you have been contacting me directly and getting some doubts cleared, and there have been some excellent questions uh, coming through those emails as well. However, I would like to discourage you from doing that because um, it becomes this one-on-one interaction it becomes very tedious. And I would not have the bandwidth to do such question and answer session on a one-on-one basis. So what I would urge you to do for those of you who have been contacting me directly, I would like you to actually put up your questions in the discussion forum because when I respond to that, or even the TAs could respond to that, when we respond to that, it benefits the entire student community. And so I would not have the same question asked by multiple people and having to respond to them individually. Okay. So please try to use the discussion forum a little more. Okay. Um, so I suppose this is an open session. The students potentially ask questions. Anirudh, I see that you have some asked some questions. Thank you for those questions. I will address them. But before we get into those specific questions, if you had any general course related questions, I could answer that. Also, maybe you
Yes.
could mute for a little while.
Yes, sir. It is a mute only, sir. Dear learners, if you have any questions, you can ask directly regarding this sessions or maybe related to general query about courses, like this course.
Okay.
Yeah.
Um, so, for those of you who are already tuned in, are you able to hear me clearly? Just do a show of hands.
Okay, I'll change something. Wait. Yeah. Give me some time. Yeah.
Yes. Oh, yeah. Ankur's voice is poor. I think there's some bandwidth related issue. Ankur, maybe you can turn off your video and when you try to speak. Maybe that will conserve the bandwidth. Maybe the voice will come out better. Okay. Mm. Oh, okay. Anirudh, I see that these are not just about what has been taught so far, but also what is coming up in future. But that's all right. I can still answer those. So the first question is, what is fluorescence, and whether that can happen during stimulated emission. So fluorescence is the phenomena that happens when you have a certain system where you are giving energy to raise an electron from a lower energy level to a higher energy level, and that from that higher energy level, if it is emitting light, that general process is called fluorescence. And generally, fluorescence is associated with spontaneous emission. And of course, it's stimulated emission. You're stimulated by a incoming photon as well. So you have a more coherent interaction that's happening. But even while stimulated emission is happening, you could have certain electrons in the higher energy level coming back to the lower energy level. So you could still have spontaneous emission. So you could still have fluorescence while actually having the stimulated emission. But like I said, fluorescence is associated, or fluorescence is in general associated with spontaneous emission of light. Is that good, Anirudh? Is that what you were asking for?
Yes, sir. Yes, sir.
Okay, good. So the other question that you asked is what exactly is non-radiative relaxation, and how is a phonon related to non-radiative relaxation? And both those questions are interrelated. So you are exciting, let's say, an electron to go from the ground state to an excited level, right? But that level is, suppose it's very close to another energy level. When I say it's close to energy level, how do we quantify that? If the energy difference between these two energy levels are comparable to the vibrational energy of the medium, and the vibration energy is what is otherwise known as phonon energy, then you have a high probability of non-radiative relaxation. So let me just quantify or sort of qualify what vibration energy I'm talking about. Any atomic system, for example, will have these two atoms that are sitting in these two positions, and at room temperature they are not actually, and they are actually sharing a bond, let's say, but they are, so that can be looked upon as two masses connected by a spring. But at room temperature, these atoms are not going to be at the sitting idle. They're going to be actually, you know, moving around their mean position. So it's almost like these two masses are essentially moving around their mean position. And in that process, you have basically certain vibration energy that's corresponding to this movement, and that vibrational energy is what we call as phonon energy. Okay, so this phonon energy could be a way of de-exciting this electron from a higher energy level to a immediately lower energy level. Okay, and so essentially this electron energy is given to the material as vibrational energy, which eventually gets dissipated as heat. So it is not, that energy loss over here is not going to be corresponding to light emission. Okay, so that is what we call as the non-radiative relaxation, as far as this atomic system is concerned. Did I answer your question? Do you have any further question on that?
Yes, sir, but does it generally mean temperature? Like,
Yeah,
does it
yeah,
involve phonon with
right,
temperature?
right. So these vibrational modes are actually a function of temperature. The number of vibrational modes, the number of phonons that you have in the system is increasing as a function of temperature. As you give more thermal energy to the system, then you have more number of these phonon modes that are excited. And so you can argue that the probability of non-radiative relaxation increases as you increase your temperature. So from that perspective, what we define as lifetime for a particular energy level in the presence of this non-radiative relaxation mechanisms, that lifetime is going to decrease, okay, as you increase the temperature.
Okay. Thank
So thanks for that question. It's a good question, right? And then there is this other question which may not be relevant to a large number of students because they have not heard of these terms. But what you asked is, what are the differences between spontaneous emission and scattering, like Raman and Rayleigh scattering? Okay, so let's actually look at Rayleigh scattering, for example. That I think everybody is familiar with because in high school physics we learn about why sky appears blue, right? So we learned that sky appears blue because the solar radiation, when it actually goes through the atmosphere, in the atmosphere you have all these density variations at a scale that's much less than the wavelength. So when you have light coming through these density variations, they tend to get scattered, and that scattering, which is called Rayleigh scattering, is inversely proportional to the fourth power of wavelength. So shorter the wavelength, more will be the scattering. And the shortest wavelength that our eyes can see very well, it corresponds to blue radiation, and hence, blue light gets scattered more than any other color, and that's why the sky appears blue, right? So that is Rayleigh scattering. And similarly, there is something called Raman scattering, where light can scatter off these vibrational modes that I talked about. Okay, they can either give energy to the vibrational modes, or they can actually take energy from these vibrational modes. However, when we talk about these, and that is what we call Raman scattering, it's named after the famous Indian scientist Sir C.V. Raman. I will be talking more about this in, I think, week 12 of this course. Okay, so you learn more about these scattering mechanisms. But nevertheless, when you talk about scattering, you are not talking about holding that energy for a long time, right? So when we talk about, let's say, light emission, so far when we talked about spontaneous emission and stimulated emission, we talked about an electron jumping from one orbital. This is the valence orbital. Let's say that's what we call as the ground state, to a higher energy level, and maybe it relaxes down to another energy level, which we call as the metastable uh, uh, state. In that metastable state, it can spend a certain amount of time. For example, in rare earth ions like erbium and ytterbium or neodymium or thulium, for example, it can actually stay in that energy level to almost a millisecond or even a few milliseconds before they come back to the ground state. And I'm talking about this in terms of, it's all probabilistic. So I'm talking on the average, it could be in the order of milliseconds, right? So you're talking about energy storage in this higher energy level, the metastable level. You do not have any such energy storage when it comes to the scattering phenomena. The scattering is something that's happening almost instantaneously. I say almost because Rayleigh scattering is directly happening, but Raman scattering, you are actually having an energy transfer, so that might take a finite amount of time, but that's inconsequential compared to the time that we are talking about, the lifetime of these atomic systems. So that could be in the order of milliseconds as far as uh, rare earth atomic systems are concerned, and it could be in the order of tens of nanoseconds when we talk about semiconductor systems. But nevertheless, those are still much longer compared to what's happening in scattering. Scattering it's almost like an instantaneous. So that's the difference between scattering of light and the other case absorption and emission of light. Is that clear?
Yes, sir. And I have another question. Like, is reflection some sort of an ordered scattering, you can say? Because I'm not able to understand how reflection works, say, in atomic scales.
So reflection is once again, it's interaction with the medium, right? So the reflection is by two ways. One is actually what we call as metallic, in what's happening in metallic medium. In metallic medium, especially if you are talking about highly conducting metallic medium, the electromagnetic wave cannot penetrate inside the metal. The penetration depth or the skin depth is extremely small. So the fields actually have to get reflected, right? And this reflection happens at frequencies that are smaller than what is called the plasma frequency. And the plasma frequency for several of these metals have appeared come about in the ultraviolet wavelength. So any wavelength that is longer than the ultraviolet wavelength, or any frequency that is lesser than the ultraviolet frequency, will get reflected. So when you are actually seeing yourself in the mirror, typically you're talking about some aluminum coated mirror, or gold coated mirror, or silver coated mirror. That's how this visible light here, you see it's bouncing off that mirror. So that is actually reflection, and there is very little, once again, interaction that's happening between the light and the medium. So there is no concept of lifetime as far as that reflection process is concerned. Okay, so that part is clear. Now the other way of reflection is through something that we saw, I think, in the first or second week of lectures, where we talked about dielectric medium, normal incidence at a dielectric medium, but the dielectric medium had alternating layers of low and high refractive index material. Hopefully you remember that we were saying that you could make a mirror by making all of these layers as quarter wave thick, so that you could have constructive interference from each of those interfaces, and that could actually add up in terms of light that's going in the opposite direction. So that is what we called as a dielectric mirror. So that is once again another case of reflection. But here again, the constructive interference happens within a very small stack of dielectric material, and that again is near instantaneous. So there is no lifetime associated with that. So reflection, once again, like scattering, is happening almost instantaneously. Whereas when we're talking about absorption or emission, it happens, it's mediated through this uh, atomic or semiconductor systems which have a certain lifetime associated. Was that clear?
Yes, sir. Yes. Thank you, sir.
Okay. And how do we differentiate between scattering, emission, and luminescence? Emission and luminescence, is together. I mean, it's emission is, it be spontaneous or stimulated emission, whereas luminescence is typically referring to spontaneous emission of light. So luminescence, once again, is like fluorescence. However, luminescence is a more generic term, in the sense that in fluorescence we're talking about light absorption and then emission. So excitation with light and then emission. Whereas in luminescence, the excitation need not be based on light absorption. The excitation could be because of you know uh, some charge transfer mechanism, which could be chemical or biological or mechanical in nature, right? So there could be, or acoustics could also, in some cases, give you this excitation to the higher energy level. And then from there, if you are looking at light emission, that is what we call as luminescence. Okay, so luminescence is a more generic term, and it's almost similar to emission of light. Whereas scattering, just as we were talking about, is basically because of like we talked about Raman or Rayleigh or Bruin scattering is it's almost like an instantaneous phenomena. Okay, there is no energy levels associated with that. So from that perspective, Raman scattering specifically is very important because you can get what is called stimulated Raman scattering, where you are coming in with a photon to stimulate this scattering process, and you can get amplification through that. But in that case, there is no real energy levels associated with that. So one of the constraints with talking about real energy levels is you can have emission only between those energy levels. So basically, we are talking about only at specific frequencies you can actually emit light, right? So um, you don't have that constraint as far as stimulated scattering process is concerned. So we will talk about this in the last week of our course, where we talk about Raman amplifiers, and these Raman amplifiers can happen at any wavelength. Compared to, we talked about erbium dope fiber amplifiers. That erbium dope amplifier is able to provide gain only around 1550 nanometers. It's constrained by the specific energy levels that we're talking about. But in stimulated Raman scattering, we don't have that constraint. Okay, so that's all the questions that have been posed to me so far. So are there any other questions? Anirudh, hopefully I answered all your questions.
Yes, yes. Thank you so much.
Sure, sure. Are there any other questions? Because I'm just getting a call now reminding me that I'm supposed to go somewhere by now. But if there are any quick questions, I can answer them before I go.
Guys, anyone having any questions? You can type
Right.
also.
Looks like what is your viewpoint on photonic chips? So I think that's beyond our course in general, but in the spirit of this course, I will tell you. So photonics chips are actually uh, completely revolutionizing the way we are looking at computations and signal processing in general. So it's just about starting, so we know from our past in 1970s, we have this concept of integrated circuits, and that completely transformed how we look at electronic circuits, and it brought about a lot of changes in our life over the last 50 so years. And we anticipate similar sort of revolution as far as photonic chips are concerned, photonic integrated circuits are concerned. So it's still very rudimentary as of now. The lot of developments have to take place, but once those take place, you will see a huge difference in the way we are doing our computing, signal processing, storing, uh, information, and all of that. So it will completely revolutionize the way we are doing things. Wall plug efficiency of these chips, they are going to be much better than what we are doing right now. A lot of things that we are doing right now, we're doing some electronics processing, and then we are looking at modulating light using electronics. But once you have more photonic processes happening, it will be much more energy efficient, and you will have, in general, more conservation of energy. But like I
Yeah.
said, there are topics that are way beyond this course, so I don't want to engage very deeply into that. Yes, Harshavardhan, you have a question?
So I also have a personal interest a little bit in quantum emitters,
Okay.
and
What is a quantum emitter?
So single photon emitters, for example, and then also, say, for example,
Everything that
two-dimensional materials.
everything that we have been talking about so far as light emission is concerned, it's a quantum phenomena,
Right.
right?
In a sense, quantum single photon emitters for quantum devices in general. So my interest is in
Yeah,
quantum devices.
yeah. So if you go to the single photon level, then the statistics become more fascinating, and it's you cannot predict at what exact instant or what exact frequency or phase that this light will be emitted. So it cannot be replicated, and that's why quantum phenomena is very interesting. But all the discussion that we had is all basically quantum phenomena. So that way, although people throw these big words at it, all that could be abstracted in the physics that we discussed already in the course. So don't get you know intimidated by all these words that people use. Okay. So with that, I will actually sign off. I need to attend to some other business here. But as far as this interactions with the TA is concerned, Ankur has been doing a great job, reaching out to you guys and helping you guys. But I feel that he's been helping a little too much. From what I understand, he's been actually giving you the solutions also, and some people are getting very used to seeing those solutions. So even if one of his sessions is missing, there's a lot of complaints about that and all that. The idea of this session is not to give you the solutions. Okay, this is something that I told Ankur just now also, is to give you some hints as to how to work out those problems. But I do want you guys to put your own effort to going back and looking at the videos and figuring out the solutions based on that. Okay, so please do that. Please watch the videos carefully and try to learn from that. So today you may have a Ankur to help you with the solutions. Tomorrow when you're sitting in that final exam, Ankur is not going to be there with you. Okay, please keep that in mind. Try to work out these solutions yourself. Shivardhan, you have a question? Quick question, please.
Yeah, it's kind of a suggestion. Although there is transcript available, but on the video, is there any way for you to kind of put bookmarks for the topics? Because it gets really tedious to scroll back and forth, and they all look the same, and we're talking with the same video screen for a long time. So the
Yeah.
time pointers would be really helpful.
Right. No, I understand. I think that's a job for the TAs also. They could probably put a bookmark, in the videos. Thank you for the suggestion. It's a very good suggestion. I will tell the TAs as well as the NPTEL people to see if they can implement that. Thank you. I really got to go now, but it was great interacting with you guys today, and look forward to the next opportunity to say. Take care, guys.
Thank you so much,
Over to
sir,
you, Ankur.
for joining. Yeah. Okay, sir. Thank you so much. Guys, my voice is audible now. Hello there.
For your voice has dropped quality.
Okay. Now also it is
Let's
not
try to
audible
bring.
properly.
This is better. This is better. This is
Yeah, yeah. I think my screen is visible now. The thing is like, yeah, okay. Yeah. Just a second, I'll just use my phone audio. There is some issues there. I don't know like why it is not audio is not audio like not connecting through my phone. I feel like it will be audible for you if I'll talk loudly. Robust. Maybe better I'll just turn off my video so maybe it is audible now. Okay, so yeah, sure, Harshvardhan. So I'll just today I will discuss about this live session problem, week 8 problem we can say. So whatever you have, as professor told already, like it is not good to reveal the solution, all the solution, and that could not be useful for you in a final examination as well. You will mentally not prepare. You will be not mentally prepared for that. So I feel like I should just give like whatever you have doubts, I'll just solve the doubts. So that could be better compared to this solving the assignment because whatever the assignments questions are there, all are taken from this videos lectures, professor's video lecture. So you can follow those things. So please let me know what you have doubts regarding this week 8 assignment. One by one questions we can discuss. If you have doubt, you can just type or you can talk. Please go ahead. Okay, in question number first, I'll just read about this one, what they have asked and what you have to do for that. So estimate the modulation bandwidth of a gallium nitride LED if the carrier lifetime is 2.65 nanometers. Suppose it is the carrier lifetime is 2.65 nanometer. So you have to uh, calculate the modulation bandwidth. What is the modulation bandwidth? F3 dB. Like the formula and everything is given in lecture. You just follow that. Necessary things, whatever you have in your mind, you can ask.
So, Ankur, do you have any specific sort of bookmark in your mind for each of these problems? That would be really helpful. I know you're not supposed to give answers, which is all right, which is perfect.
Yeah.
But at the same time, we come here because we need a little extra help because we couldn't find it in the things,
Yeah,
or
if you'll
sometimes we have
follow,
not
no
able to
better,
touch the thing at
like
all.
you should make a note, like whatever the lectures are given there, that notes you will like you will write one by one portions. Okay, so that will be better. So you have to follow this
After
week
teaching
eight.
11 hours, it becomes difficult to learn another 11 hours. Like, we are doing it as a secondary profession also. No, it's not like I'm
Yes,
student
yes.
all the time, teaching also.
Yeah, I'm
So from
understanding your concern. The thing is like you have to give a final exam also.
right,
Those
right.
things it is very difficult after that.
Bookmark in the
So
video is like a bookmark book. That's
y-
helpful.
I can say that I don't have any bookmarks here. Like I can say that it's like a VCAT as a like videos. I can say that semiconductor light source and detector LED characteristics. You can follow that video. In that you will find out the solution because generally we don't have exactly particular bookmark. Okay, so you have to just here what you have to calculate this. modulation bandwidth. Got it? Then after that, you follow the lecture, you will get everything. Okay. So as per the professor's concern, I can't reveal the answers and solution now. It's very difficult for me uh, um, to help you directly on this assignments. Okay. So either it could have been better that I could have solved this already completed assignments, but um, submission date is like 2 weeks something, and between that, already it will be running. It will be going on this week's assignment. So that's the thing. Okay, so here the question number question number 2 and 3 data is given below. So use the below data for question 2 and 3. So it is given like 0.35 gallium Indian gallium arsenide phosphide semiconductor laser refractive index is having 3.6, has an internal loss of 20 per centimeter inverse, like 20 per centimeter, and the reflectivity of the mirrors on either side is 90% emitting at a wavelength of 1350 nanometer. So here this question number 2 has asked that the minimum gain required to compensate for the losses in the laser cavity is. You have to generally you have to like all the uh, things has been given. You have to first you have to calculate the what we can say that minimum gain required. So that is like gamma. So your minimum gain should be that will be a formula in this same video lecture. You can follow for that semiconductor light source and detector laser characteristics, and in that you will get this gamma value like formula. Through that you can solve this one. Okay, and second question is that FSR range between the longitudinal mode of the laser is in gigahertz. They have asked up to 2 decimal accuracy. Both places 2 decimal accuracy they have asked. So in that FSR you have to calculate. So FSR is like it is a straightforward question. So you don't have to. I think it's not interrelated. It's like both are question individual, but data is common. So you can follow this both questions one by one. Did you got it? If you have doubt in like after solving, you can ask in next week also, if it is possible. Okay, guys, you are listening me? Yeah. So better to go for lecture by lecture. That will be easy for you. Okay. Then we have question number 4. Here the question is a semiconductor laser diode refractive index of the gain medium is 3.6, emitting at a wavelength of 850 nanometer, has an internal quantum efficiency of 0.45, and the threshold is achieved at 580 milliampere injection current. The output power of the laser diode at a drive current of 600 milliampere will be. So first you have given this threshold injection current, and you have given the drive current. Everything like it is given here. Refractive index is given. and wavelength lambda is given. Efficiency, um, um, it's like internal efficiency we can say. Internal efficiency is given. So you have to calculate the power, output power, how much it will be. Okay. And okay, so okay, just follow the lecture one by one, so you can understand the solution. What could be the solution? So here, what you have to do, you have to just first you have to be calculate the output. Sorry, external quantum efficiency. Eta out you have to calculate, and you have to keep in this equation, or whatever the formula is given in the video lecture. You can follow that. Okay. And the question is, one second. Question number 5. The question is the assertion according to the chronic penny model. The potential of an electron in a crystal changes periodically, and the reason is the potential of the electron is zero near to the nucleus and the maximum, and is maximum between the two nuclei which are separated by interatomic distance. So here, chronic penny model you should be understand. So it is a straightforward question. You don't have to follow the lecture as well. If you have uh, if you have solved this, maybe this model is like or electron transport from this crystal, like perfectly crystalline material. So in chronic penny model, what will happen? Um, like positive nuclei will be there, and like this, and you have this potential well here. So when this electron, suppose we have electron, it is moving from here to here, so it will feel some this part and this part. It will be like uh, potential will be very less, but here this area it will be very high in between the two nucleus. So that is telling the uh, thing about these electrons, how it is periodically changing in a crystalline material. Okay, while it is moving from one direction to another direction, that is given by the chronic pendulum. Before that, people were thinking like it is in crystalline medium, it is going like just on surface, it is going without any have, having any barrier, surface barrier potential. You can say. Suppose we had nucleus, so electron was moving just like that, but no, it's not true. It's like it's having some field. It's feeling some potential between two nuclei. Okay, you can solve this problem seeing that one by one. If you have doubt, you can ask directly also. So assertion is right. Uh, uh, Follow this lecture. Better to like. If I'll comment again, then professor will having he already told strictly. So better to follow the lecture. It will be easy for you. I feel like it is from lecture only, so you will understand everything. Whatever we are discussing, everything is in lecture. Okay. Chronic Penny model, like I already told, this is in crystal, so we can understand these things. And reason also, I told that whatever it is having here. Okay. So near to nuclei, it is feeling zero potential, and if it is going between two nuclei, it is feeling like maximum potential. Are you getting my point? Then this question number 6 is there. So find out whether the statements are true or false. So first statement is the Fermi energy level is closer to the conduction band in a phosphorus doped gallium material. You have to think about this phosphorus doped gallium material means what? Tell me, like if you dope phosphorus in gallium material, it will be N type or P type semiconductor. P type, how you can say? So nitrogen family, phosphorus is a nitrogen family member, family group material. So it will having a pentavalency. And gallium, it will be, yeah, better just go through this lecture. You will get to know like whether it is a P or N. See, it is a like pentavalence, so pentavalence will be having N type semiconductor. Are you getting my point? It's electron rich. So through that you can solve this problem. Fermi energy level will be closer to conduction band or a valence band. You know, conduction band will be upside and valence band will be downside, and Fermi energy level will be in the middle of the both conduction and valence band, while it is a pure what we can say silicon family group member. Are you getting? So based on that, you can solve this one. Then the statement two is that the aluminum dopant and silicon accept electrons and increases the concentration of the holes in the valence band. So what do you think about this one? Are you getting my point, Sabapati? It is not a P type. Am I audible? Harshvardhan, am I audible? Nobody is telling anything. Yes, it is audible for you. Everything. Yeah. Okay. Then statement two is telling that this aluminum dopant and silicon. Again, you have to go for this. It is an N type or P type. Okay. So, can you comment on this, Guru? Guru Charan, Charan, Guru Charan? If you have aluminum dopant silicon means it is an N type semiconductor or P type semiconductor? Yeah. Yes. It's a P. So you can, based on that, you can see whether it will go. This Fermi energy will go to the toward the valence band or conduction band. So what do you think like here Fermi energy level is going down or up? Because you have two is conduction and here valence. So Fermi energy will be here for this pure silicon family group member. Okay, if you are doping with N, so it will go up or down. Yeah, it's like you are increasing holes in the material, whatever the semiconductor we can say. If you are increasing holes, then it will go to near to the valence band, and number of holes will be high, and it will go for this um, N type. That means like it will go up. Fermi level will go up. More electrons will be there. It will feel more. Okay. Like this. And here it will be P. Okay. After that, question number 7. Okay. So you just follow this. You'll get to know like whether it is correct or not. Follow the lecture. This lecture is cancel that. A second. Yeah. So this lecture is semiconductor light source and detector band structure. Okay, it will follow this one. And you'll get to know this. Then question number 7 is there. In that, in the given PN junction diode, what is the charge density and the electric field distribution corresponding to the depletion region? So here you can first you have to find out whether what is the charge density. So you can see here this area, this all are given as a charge density. Okay. So all you have to follow one by one which one is correct for that. You can also predict now itself. What do you think? Charge density will be higher in positive side or negative side? It seems like you don't have any doubts or you don't want to interact. Okay, then after that, electric field distribution is given. So you can see that electric field distribution, the second option B is the electric field distribution for that. Change color. This one. Okay, this is given as the electric field distribution. So in the junction, this junction it is having. It has been asked what will be the charge density, like this side and this side, and what will be the uh, electric field distribution at the junction from both sides. Okay, so this line is showing that it is a junction. Okay. Each side it is having what charge density will be higher, like that, something like charge density positive or negative. It will be it. Uh, you can predict here itself. While you see the lecture, which is okay, yeah, semiconductor light source and detector light emission. Light emission, that lecture you see, in that is exactly mentioned how it could be. Okay, just follow that lecture. Okay, yeah, better. Then we'll go to the question number 8. Here, match the following semiconductor material, column A, and their corresponding absorption emission characteristics, column B. So what you have to match is semiconductor material and their absorption emission characteristics. So silicon, what could be the absorption or emission we have to check. So how you can check? You can't predict just like that. You have to follow all this. For all these things, you have to follow lecture one by one. It's not a predictable. So go through the lecture. Professor has mentioned everything, and for this also it will be like, yeah, it will be like semiconductor light source and detector light emission. So question number 8 also you can follow this one. Okay. Now this question number 9 and 10 has given to see common data, that is a forward bias of 2.7 volt is applied across a gallium nitride. Refractor index is 3.5 near UV LED 380 nanometer. Okay, so 380 nanometer. To drive 50 milliampere current, the internal input efficiency is 50% and the carrier lifetime is 1.3 nanosecond. So what is the internal photon flux for the above LED? So you have to find out the internal photon flux. Okay. So driving current is given, internal efficiency is given. Then you have to just keep all these things in equation that you will find out through the professor lecture itself. And now after that, this question number 10, the last question of this, is determine the LED's power conversion efficiency in percentage. So you have to note that the power and conversion efficiency is defined as a ratio of the optical power generated to the power supplied electrical power. So the energy efficiency, like sorry, a second. Now, yeah, to prove that whatever you told that is positive side, yeah, you can follow like that only. Then this power conversion efficiency I'm telling about this question number 10. In that, what you have to do is first you have to calculate. Just okay, again it left. Power conversion. You can go through this only. That will be, I think it is audible, like visible for you. Yeah. So here, this the refractor index, internal photon flux will calculate from that question number 9, and this internal photon flux, refractor index, and the external efficiency all these things and wavelength. You have to keep everything, and that formula will be there in lecture. The same lecture, semiconductor light source and detector light emission. In that, we have to calculate first power output, how much optical power is coming out. Then that optical power output is coming. That you have to, for efficiency, we can say eta consumption, or something we can say like power conversion efficiency. Okay, power conversion efficiency will be is equal to P out in optical and power whatever we have given in a voltage, but like current at a particular voltage, that power input, electric power I'm telling, electric power. And that's how you can calculate here the power conversion efficiency. Okay, in percentage you have to calculate. So it will come in a like numerical value. You just multiply with 100, and that's it. Here we'll finish it now today. If you have any doubts, you can ask directly. And better you prepare for next week as well. Some doubts or something. First itself you clear by yourself by watching the videos, professor's lectures. If you are not getting any answers or something you have, it is troubling you, you can follow this, like you can discuss in this live session. And one more thing, I will share again that question link that is, okay, so whatever doubts you have, you can ask in that. Okay, please follow this link. Okay, what is there? 90%. Harshvardhan, what you are talking about?
No, no. In the middle, I lost your voice because maybe you didn't speak only. You started a sentence and you just stopped talking, I think. So I thought
No,
I
no.
lost voice.
Okay. So this 90%, what you are talking about, I am not getting.
That was trying to get that LED question because usually the LED power conversion and efficiency was about 90 by general knowledge, but I did not do a calculation yet. So I'll do that and
Okay.
then come back to the answer.
Yeah, better to the last question you are talking about. Power
As-
conversion efficiency. Is it that question number 10?
yeah. 10 last LED question. Yeah.
Yeah. It's not like 90% we can say you have to calculate. It could be 1% also. It could be 30% also. The thing is like how like whatever the given out input and whatever the output you are getting, so that it matters. Okay, so 90% it is possible, but I don't think so. Here it is this much efficiency. Okay, you just calculate one by one things. Output power you
So
have to
this
calculate. Huh?
particular problem is based on a particular LED or something because I mean I know I have been reading papers about different types of LEDs whose power conversion efficiency is very close to 90. So which
Yes,
LEDs
yes.
are we talking about?
It is not a like it is a hypothesis. Whatever questions is given, it is based on the numerical values. Suppose you have numerical values that is giving the power optical power output is like 10%, and we can compare that commercially available. Companies are having doping something and increasing this efficiency, quantum efficiency to some. So here, the internal quantum efficiency is around 50%. Suppose they have like 60% or 65%, it is possible.
Yeah, yeah, yeah. No, no,
So
I
based on
had,
that,
yeah.
uh,
That's what I said. My mistake was I did not connect this to the other data that is given on
yes,
the
yes, yes,
top of that ninth one.
yeah,
That's why I was having
yes,
confusion. Now I got it.
yes.
Yeah, yeah.
Yeah. So carrier lifetime also matters and bias also matters. So if you're giving more bias, maybe possible it will give less efficiency, or possible like particular at threshold it will give very high possibility for power conversion. So efficiency is matters on this particular data, whatever we are giving, and we have to like in research purpose we it is like like so many things we have to change. Bias we have to change, quantum efficiency to increase that, doping also, all these things will be matters. Only particular gallium nitride won't work. Here we have to dope something n type p type, then it will be efficiency will be 90%. So here only
Yeah, yeah.
numerical values you have to calculate.
Yeah.
You don't go
Thank
for
you. I got
like
it.
actual value like that, okay?
Yeah, I got it.
Don't think, okay, like that you don't. Just whatever questions you, and if you have any doubt regarding this also, this assignment in future, you just go through this Google link, form link I sent just now. Okay, I'm sending again one more time. So keep in mind like whatever questions you have, just keep it there. If I feel like this question is not understandable for you, then I will help you surely. Okay, that you don't have to worry about this. But you have to solve something and you have to send whatever you have solved, something like that. Are you getting my point? Yeah. So this session will stop here itself. If you have any doubts, please let me know just now, so I can help you in this one. Okay. Yeah. Thank you so much for joining. We'll meet in next week at same time. Okay. Yeah. Yeah. He will join maybe sometimes more. I'll encourage him to join more, frequently, weekly, like at least 5-10 minutes something. So it will be useful. Okay then.
Thanks.
Yeah, yeah,
Bye.
yeah. Bye as well.